I'm really excited to be here to share our story of using HPC for our engine project actually at our center. So my name is Yuanjiang Pei from Aramco Research Center, Detroit. I believe some of you met Oscar, right? What Asian ages you are from, right? Still working on engines. So actually this morning I added one more slide, basically run a reality check. So if you look at these slides, basically it's a very recent projection from IHS for the next like 30 years, or how the world looks like in the passenger transport sector, right? So you have these OECD countries, basically the developed countries. You have China in the middle. Is very special, so because the government pushed really hard on the battery electric vehicle, right? And you have the rest of the world, mainly developing countries. So this is an estimation, right? So you have the EV on the top, this light blue, and you have this plug-in hybrid, and ICE. The rest of three all have this engine actually on the car. So if you look at a different scenario, like for the OECD countries, still majority of these passenger cars still have the engine on it, right? Even for the most aggressive situation like China, they still have lots of probably like 80% have like an engine on their passenger transport car. Not to mention the rest of the world is dominate. So even like in this kind of just run a reality check in the next 30 years, still this petroleum-based liquid fuel still the main source of the energy for the passenger transport, right? This is just the passenger transport. Then going to the commercial transport, so the situation probably even kind of has even definitely dominate for using the liquid transport fuel. Okay, then let's go to my presentation. So the work have a lot, this is a truly team effort. A lot of people contributing to this work. So I want to acknowledge a few people at our center, Aramco, and also our collaborator at the Argonne National Lab is mainly from Sibindu Som's group. It's Pinaki Paul, OP, Oyela, and Sibindu Som. And also we have a collaborator from Friendship System. They mainly kind of have a very capable software to help us to properly manage the design space. And we also have Dan Provost, Kelly Snickel, Eric Pomeranian, Keith Richard from Computing Science. They have a safety software, commercial software. I'm give a little bit information why we're using it. And also the Advanced Engineering System Integrity team from Cummins for their technical inputs. So it's the talk is about using HPC, right? So we use extensively of Mira. Actually, now it's become a standard process in our daily job, actually. And also we also acknowledge the IT department at Aramco Service Company for their technical support of the cluster. So I want to spend a few slides to kind of give you an idea, okay, who is Aramco, right? So we basically was the largest oil exporter and the 6th largest refiner in the world, so with some recent purchase in the refinery industry. So we also have like a large reserve of natural gas. That's probably some like interest in the future. Okay, sorry. So we have a lot of research activity, including upstream, downstream, and also structured domain. I'm probably not going into too much details on like upstream. I mainly kind of focus on where the Detroit Research Center am, right? We are in this structured domain. Basically, we have in the field technology division looking at how to use energy in a more sustainable way. So the way we achieve this, try to achieve our mission, our goal is we work collaboratively with the relevant stakeholders. We have the headquarters. We have the headquarters at Durham. We also have like 3 research centers around the globe. One in Detroit, one in Paris, and we also have recently opened one in Beijing, and we also have one at a cost. Then work with collaboratively with the university, national lab, policymaker, OEM especially, right? We work closely with the automotive OEM to achieve the mission, how to kind of use energy in a sustainable way. So a little bit more information on our Detroit Center, right? So we focus on 4 areas in the Detroit Center. Look at this, doing some strategic analysis of a future perspective of the transportation. And we are looking at this kind of advanced technology in the passenger transport sector, and also doing some commercial transport research as well to look at the kind of co-optimization of fuel and engine to achieve the optimum performance and lower emissions. And we also have this technology integration research there. Then the CFD and HPC actually mainly falls in the two in the middle. We're supporting this, our team is supporting this passenger and commercial transport, basically looking for the really advanced engine concept that can achieve fuel like a low greenhouse gas emission, and also achieving a low like a fuel efficiency. That's all basically our goal. So our center is quite new. It's inaugurated to end of 2015, still less than 4 years old. So very briefly, right, we have a 5 state-of-the-art test cell to really demonstrate the hardware, the performance, and we also have a 4-wheel climate chassis dyno to put the technology in the engine to really demonstrate the concept. And we also have our own controller. That's really important to kind of, otherwise you're hard to kind of control, because control is really important piece of this new engine concept. And we also have an excellent computing capability there, especially working with the experts at Argonne. So going to the project, right, I want to give you a little bit background on what's the background, why we're working on this project. So this is a project in the commercial transport area. So the reason we are working on this is, so this figure basically shows a fuel demand ratio in the next 30 years. So basically a fuel ratio of this middle distillated, you can consider diesel versus gasoline fuel. So in the, we can see by 2040, this fuel ratio might reach 1.7 from different projections, right? So this demand imbalance might likely to produce a price imbalance, right, between these two fuels. So if gasoline becomes cheaper, then how should we deal with it, right? So finding ways to burn this gasoline fuel in this CI, like a diesel engine, compression ignition engine, become very economically attractive, right? So on the other hand, also there's a regulatory requirement, mainly from the emission side, criteria pollutant side, right? So CARB represents California Air Resources Board, so they are the world leader to making this emission regulation, right? So rest of the world usually follow that regulation. So if you look at their footprint for the next phase emission regulation, just look at the NOx emission, right? Just look at the NOx emission here. Right now we are at this 0.27 gram per kilowatt hour. So in the we haven't finalized these details, right? But in kind of a less than 80 years down the road, it's going to reduce 1 order of magnitude on the NOx emission. That's really a challenge. So also kind of you can't keep increase the cost to meet this not in a cost-effective manner to reach this target, right? You have to find the ways to kind of economically in a cost reasonable way to meet this emission target, and also in the fuel efficiency as well. So that's we are working on this area. This gasoline, bring this gasoline in the compression ignition actually seems not a bad way or good way to achieve this goal. So that's why we're looking at this. So the test engine we use is a Cummins engine. It's a very modern engine, very efficient. In US, probably I forgot, is every 1 in 5 or in 3 the truck running on the freeway actually using this engine. So we really, the one message you want to keep in mind is it's a really efficient engine. I think it's about 44% of brake thermal efficiency. That means even 1% of improvement based on this engine on fuel consumption is really challenging. So that's one message I want to keep in mind. So we also look at different fuel options. So I think probably some of you know that DOE has this co-optima program, right? This is basically similar. We try to co-optimize engines, the hardware, and also the fuels to achieve the optimum, to see what's the potential there. So you can see here we have quite some fuels here. You have the diesel, this kind of the market diesel, the traditional fuel we're using in the engine, and you also have different gasoline fuel as well. So they all have different physical, chemical properties, right? You have tailored the design to match the physical and chemical property of different fuels to achieve the optimum. That's present the opportunity, right? You have so many combinations, so many dimensions. You need to find the optimum combination, right? That's kind of why we're using the supercomputer here to help us deliver the project. So how to achieve this? We use an analysis-like design process. So this is a kind of very brief overview of the process, right? In the first part, we use a safety-guided design process. Safety-guided design process basically gives us like a initial combustion recipe, and then we put the initial idea into the hardware development phase. Then we get the hardware, and finally put in the engine dyno for integration and testing. Then we got the results. Then we feed into the first part. This is the iterative process, right? Then we will check, okay, what we're still missing, which part we can still improve. Then in this process, we keep refining our model. That's very, very important, right? So we work with the cost. They're really good at this chemical kinetic part. Then we also work with Michigan Tech. They kind of run some really high fidelity spray, help us to calculate spray, then help us to refine. We're going to further refine our spray models as well. So also work with the Argonne team. So that potentially will be a spark plug engine in the future. So we definitely need a really high fidelity capable ignition model as well. So then this is because the simulation run is a supercomputer, right? There's massive simulations there. So we need a really very advanced post-process tool to handle all these post-process part as well. So basically we have this state-of-art analysis design process. It's really important. We need this process in place and to enable full load range operation, not just look at one operating condition, right? It has to be robust full load range operation. Then we zoom in a little bit to the first bullet points there, so the box there, this safety guided engine design analysis process, right? So that's how we work here. So this kind of highlights the whole process, right? So in the first part, we need to properly define the design space. That's very important. Sometimes probably just the simulation is enough to just define this design space. Sometimes you really need to work closely with experiments to screen and narrow down the range, then properly define this design space. I'll give you a little bit more details later. So we use cases. This software. It's really capable. The reason we choose them is you can see this is a piston. We cut it right in the middle, so you can really capable to handle all different wirings of this design. This is just one example, right? In the top, this is the injector. This is a very important piece of in the engine, right? We also need to optimize it. So right now we rely on this case software to help us significantly improve our productivity in handling the design space. Then when we have all the designs, like 100 design combinations, then we'll be using the mirror at Argonne to run this simulation. It's really efficient. I also have to give lots of credit to the Argonne collaborators, David and also Sven, right? And also Convergent Science. They spend years of research, try to improve the code scalability and I/O performance, memory utilization, load balancing. There's a lot of hard work research there to really make this a robust process, run all these simulations in a capacity fashion on the supercomputer. Then after this actually significantly reduce the time to design, right? So usually you have so many of these designs, you run the traditional cluster, probably takes months. So I'll give a little bit more details later. Then using a supercomputer, then you can significantly reduce the time, probably days, weeks, you can get the design. Then finally, we collect all the results. In this part, we have two methods. We have the traditional response surface model. That's the most popular in the industry, and they already use it for tens of years, right? So it's kind of sometimes they're kind of very conservative. They don't want to make a change. For us, we need to try something new. So we also try to look at the machine learning as well to see if it can help us on this design part to further reduce the design time. Then we finally get a design candidate. Then we kind of find the design, we deliver to our the service provider for hardware fabrication, and finally do the testing. So before, I also want to give like some more information here. The engine simulation, probably not all of you kind of know how engine simulation looks like. I want to immediately kind of try to emphasize some challenge when we do this engine simulation. So first, when you look at this engine simulation, right, there's moving parts, right? That's a really highly transient process. You have the PC moving, you have the valve opening, closing, and you have the fuel spray injecting the cylinder in a really high speed. This really high transient turbulence, and also including combustion emission. It's a really complicated simulation. So it also, if the injector, right, I'll give you an idea. Like the injector for one nozzle diameter is about 100 micron on that kind of a length scale. But for the cylinder diameter is a 100 millimeter length scale. So it's a large disparity of length and time scale here you need to handle for this engine simulation, right? That's also very complicated physical sub-process, right? You have the fuel injection, you have the spray, you have the evaporation, right? Just to give you an idea, okay, how a spray, even just for spray, right? Even just for spray, this is a kind of a schematic of a spray, right, from one plume. Then you need to consider how you inject the spray into the cylinder and how the spray break up coalescence and collide, and how the spray, how the vapor into the vapor phase, how you interact with the turbulence, how the chemical kinetics looks like, and finally the emission, right? There's a lot of details here. And also, because we're doing the fuel engine co-optimization, we also need to consider the fuel variation as well. And then associated with it, you have the chemistry there. There's a lot of details, chemistry, right? And also emissions. And finally, there's also load balancing. So why I want to see the load balancing here is, in this slide, okay. So the code we are using is called Convert. It's a commercial code. I think a lot of, probably many of you using open source code, you might ask why we're using a commercial code here. So the reason really is that in the automotive industry, most of the OEM, right now they're using commercial code. And I would say dominant user, dominant like the Converge dominated the automotive industry. So that's for Aramco, we want to work with OEM. So we're using Converge. And also another important reason is a really powerful software. So the part we like the most is this very advanced, innovative AMR, adaptive match refining. That's really important. So like I mentioned in the last slides, you have a huge domain. You don't want to have a uniform mesh across the domain. We cannot afford it, right? We have so many simulations. So you have to only refine the region that's of interest, or leave the other regions kind of relative cost. Then you can better handling the computation time, right? So this is a jet cross flow here. This is a jet cross flow here. You can see how it deal with this mesh, right? Like basically update the mesh refinement in every time step. It's a very advanced software. So we really like it. This is kind of list all the kind of sub-models we're using. So there's a lot of things you need to improve for sure. That's why we work with the National Lab, with university, try to improve some sub-models. Okay, let's go to the final application. So with the background in place, so we did this co-optimization of fuel and engines. So we have a couple of applications. The first one is this mixing control combustion mode. It's targeting for near term. We want to see, okay, what's the potential there? Fuel consumption improvement potential there if we're meeting the current emission regulation. The second part is low temperature combustion mode is for the next down like 7-8 years down the road, we have to meet this low emission standard. What's the potential there, right? Okay, let's first look at the first application. So that's what we got following this HPC-based engine design optimization method. So that's what we got from the simulation, right? So this basically shows the fuel consumption improvement. So this is for one design. So this is kind of a combination. We can got like a 4.1% improvement over the fuel consumption. That's from the prediction. So this shows basically different parts, right? We kind of breaking down, okay, which part contribute how much. Look at the fuel consumption improvement. Then we deliver and we do the hardware fabrication and we put hardware in the engine, do the testing. That's what we got. With different combination, we can achieve from anywhere from 3.2 to 4.2% improvement. So basically, we can achieve up to 4.2% fuel consumption improvement. So there's a couple of messages here. First, seems kind of they are on the same order of magnitude with the prediction. That's really encouraging. But we definitely need to look in details to see what we are doing well, what we are missing to further improve, right? So that's one message. Second message really is this high fidelity CFD simulation really accurately guiding us to do the engine design to achieve our goal and meet our timeline to deliver the design, deliver the project. And this is in a much cost-effective way, right? You don't want to test all the hardware combinations, right? In hardware, that's too expensive, right? So that's really encouraging when we see this. Then how about the second one for the future low emission standard? So for this one, it's more challenging. So the reason is for the design space I mentioned in the previous slide, right? The design space you have to be carefully characterized. You cannot just rely on simulation. You have to work closely with experiments then to properly design this design space, because we have so many fuel combinations here, so many fuel here. We want to see, okay, which fuel gave some promising, then help us kind of shrink down the design space a little bit. So with a lot of work here to help us properly define the design space, and this finally what we got, right? We got like up to 6.3% fuel efficiency prediction. That's our prediction. So right now we already got some hardware, part of hardware. We're still waiting for one or two hardware coming in. Then we're going to next month, or we plan to do our integration testing. Hopefully we can finish the story for this part as well. So that's kind of we use the HPC to do our design, to kind of guiding the design process, help us to deliver the project. So what if we take a step further to see, okay, how the machine learning can help us here? So we work with Argonne's group, with computer science as well, to give a shot to see, okay, what's the potential, what's the possibility there, right? So there's this new method called machine learning genetic algorithm method for engine design. So the motivation really for us is we did a design which use a traditional genetic algorithm method to do the engine design. We tried out. It turns out we found is along the process we found it's a nice method, but it turns out it needs a lot of generation to converge to get an optimum design. It's a very lengthy process. And also when you consider the real application, you have so many operating conditions. You combine all these operating conditions, it makes the process even longer. So that's kind of something we cannot afford, right? So they motivate us to look at, okay, can we leverage high performance computing or supercomputer to further reduce the design time? That's kind of this method was proposed, right? So we basically using a supercomputer to run a bunch of simulation. For this project, because this is the first project, we run 2,000 simulation as a training data for the machine learning. And then it's reduced. Actually, if you run this simulation is on cluster is too long time, right? Like a month, maybe half a year. But running on a supercomputer can really achieve with like weeks, right? A couple of weeks, maybe you can finish all the simulation. Then we through this 2,000 simulation as a large data set for machine or training, and then we actually found out maybe like we have 9 design variables, probably 250 probably is sufficient to do the training. And then we actually compare to the traditional methods, traditional CFD GA method. We found it's a pretty decent, very good results. And actually, it can help us really significantly reduce the design time, right? That's kind of provides some another way of looking at this engine design, right? Using machine learning. Then we also further extend a little bit. That's kind of in the previous project we look at this different design parameter like boundary condition. But here we extend a little bit. Okay, can we probably also do the ball geometry, the geometry-wise as well? So it turns out we also use similar methodology. It turns out it gives a very similar prediction as the CFD, traditional CFD method. So it's really encouraging not just to look at some boundary condition, also the geometry-wise. So we definitely see the potential here. This machine learning can further reduce the time to design, but certainly, like I said, most of like industry, automotive industry, I would say they are very conservative, but they need time, they need more evidence to prove, okay, they can use this method. For us, for Aramco, we are a little bit more progressive, but we also have a timeline. We probably will do a couple more demonstrations to prove it is solid and robust and can work. Then we can apply this machine learning into our design process. Okay, finally, a summary. Basically, we have, for this project, we have a comprehensive engine design that's really, we have the hardware, do the testing, we show the fuel consumption improvement. Again, although the 4% looks not a big number, you have to consider this is a modern engine, really efficient. You consider the gasoline like this normal probably gasoline car you are driving. That's the BTE, brake thermal efficiency, is probably like 30% or slightly over 30%. For this engine, Cummins engine is like 44%, really efficient. Any improvement upon that is significant actually. So we see 4% is really significant, encouraging results. And also we see this accelerated design process using HPC. Right now, actually, it's become our standard design process at our research center, and we have, because we work closely with OEM, wide range of OEM. So we hope we're going to share. So for us, we really don't want to keep it confidential. So we're going to share with the whole industry, automotive industry, if they are interested, they can use the methodology. So we also see the potential of machine learning. So I think for us is we are a little bit aggressive, not that conservative, because we probably want to do a couple more demonstrative projects to see if it's solid, can be utilized in the industry. So for the future work, we're going to further streamline this whole process, this HPC-based engine design process. For example, one idea is using this Swift, right, as a resource manager to streamline the whole process, right, to make it more user-friendly to use for this design process. And like I said, we also interested in integrate this machine learning into our design process. Finally, I want to give a little bit eyes. So we have a symposium, half-day symposium called Developer Virtual Engine Symposium. So it's maybe more interesting in the automotive industry, but anyway, I just want to bring this up. It's part of the ASME ICEF conference. Actually, it's going to be in Chicago, very close to here. So basically, we're going to invite DOE and like automotive industry experts to join and share their insights on future transportation perspective and its implication to the virtual engine development. So you're welcome to join if you're interested. Okay, I think I'll conclude my talk, and I'm more than happy to answer any questions you may have. Thank you.
Questions? This one there. Okay. Oh, okay.
That was fantastic. I think you've done a wonderful job modeling the combustion process and the engine and everything. I was wondering if you had considered trying to model an engine that was closer to the end of its life rather than a new engine, to see how that might impact the fuel mixtures and if there could be some changes in the design so that as an engine ages, you maintain that efficiency.
That's a great point. I would say that's a great point. That's actually something we probably already done something. So also utilizing Argonne, the user facility, the advanced photon cells, right? So we have inject, because the injector is a really important piece of this engine part. So we see the degradation of the injector over their lifetime. So we actually run some testing, or actually try to kind of to see, okay, over the life of the injector, how the injector degraded over the life of its time. Then we did find some like a cavitation-induced erosion there. So we actually have the hardware. We have plan actually work with the Sven's group. We actually have plan try to see, okay, how this is going to be performs in the engine. That's first thing. Second thing, on top of that, right? We also have plan, because I think we all know that in the market, although you have one fuel like a 87 fuel there, but from different states, it might be very different because they're all from different refinery, right? So we also have plan to kind of look at the fuel variations on the market, try to make sure wherever you get the fuel, you're going to have a stable, still maintain the emission compliance, you have achieve the optimum performance. That's something we're actually working on. It's actually a big project in our center. Thank you, that's a really good point. Yeah.
So how's the performance of the engine? We saw with the Volkswagen scandal, they couldn't get a diesel that performed well without polluting.
You mean this engine? Yeah. So through our optimization, we have two applications. One is maintain the emission same as the stock engine. We have better fuel consumption, and also we show the potential pathway for the future low emission regulation. And while in the meantime, we also achieve lower fuel consumption. So it's pretty solid, I would say. We currently work with I would say probably 4 or 5 OEM try to look at this technology, do a demonstration.
Did your engineers have to go through any training to use the AI code, or was the code written in a language they already understood?
To be honest, I personally cannot do the coding of the machine learning part. So that's why we need the expertise from the industry, right? So we cannot look at everything. That's the thing. Yes, we have some resources, but all focus is still on engine part. So our CFD is we need to support the project in the center. So that's why we rely on the community, like the expertise, work closely with the national labs, to help us on this part.